Once again, welcome in my new video, guys. This is a part number 2 of the retaining wall, cantilever retaining wall numerical problem. So in this video I am going to deal with the stability calculation, that means the pressure distribution at the base, and the design of the hill slab. Now, as in my first lecture of the retaining wall, I designed this steam calculation. The steel at this portion, totally what is the amount of steel, what is the distribution steel, everything I calculated in last lecture. So for that, if you need to get any details about the retaining wall, you need to visit over there. You can see here the total dimension. You can see, this is a cantilever slab slim 200 mm. How we get, I just listed over there. I calculated over there. 4 meter height, how we get 5.2 meter. Every dimension what you are seeing over here, this all dimension you can the all dimension calculation you can get in part number 1. Just visit on my YouTube channel. My name is Parag Pal. You can write here like it is I can write over here Parag, P-A-R-A-G, Parag Pal. Or you just visit my website www.civilnotes.com. So it will be more helpful for you. There is lots of spreadsheet. Go and visit there. Now after this diagrammatic representation, why I create this diagram? Because you need to know about which dimension. Like you need to take a picture, or for the, you can go on my website. You can see there is this notes also there. You can take the photo from that website also. So so with respect to this this dimension, I am going to do my next calculation right now. So my next calculation is all about the stability calculations. So first of all, like I just turn this my page for the stability diagram. You can see here what is the stability diagram. It is a pressure distribution at base. I calculated over here. This is what the top, this is what the toe slab, this is what the hill slab distribution, and this is what the steam distribution. So these three things I just draw over here. If you are not familiar with this diagram, you need to watch my basic video of the cantilever retaining wall, where I just tell something about this pressure distribution. This is what about the all pressure, like this is about the retaining wall. This is about the pressure distribution at the base, how the pressure is distributed, or distribution is happening. With respect to that, we are going to design the slab. So because we design the steam, now with respect to the all dimension, we are going to design hill slab and toe slab. For that, we need the pressure distribution. If we don't know what is the pressure, how much amount of the pressure is coming on our slab, without that we cannot design the hill slab, or without that we cannot design the toe slab. So now first of all, for stability, I just take my next page also here. With respect to that, first of all, I start something different. So stability calculation. So we are going to for step number D. So it is what the stability calculations. Stability calculation is also having something like pressure distribution at base. You can also call it as pressure distribution at base. So these are the two names over here. So now let's get. So here, what is the hill projection? We need to first calculate. First we need to calculate what is the hill projection. How much amount of the hill projection over there, and we get hill projection like 2 minus of 0.45. So we will get simply the hill projection 0.45. Now how we can calculate this value, you know about, like for this, like it is our retaining wall. So this total value, this total value, we need to just calculate this hill projection. The base is what, our 450. So minus, I just minus 2 minus this one, so I get the hill projection simply. So now after that like only I am just dealing with this 1.55. Okay, not exactly. I just, that means for you need to just minus the 2, like this is not only the 2, this is not total 2. Okay, you need to remove, you need to just don't worry about this hill, only this portion. Okay, from this value you need to minus this one, so you get the hill projection. Okay, because you can see over here, this is what the hill projection you can get here, only this. So if you deal with this value, okay, it will be more simple for you. Okay, or not this 450, you can minus this 450. I'm sorry, this is not 450, that 450. So this 2 is, that means up to this value, this is what 2 meter, and 4.45 is this meter, that means hill projection steam value. So you get this much value. So, okay, now after that, overall dimension of the wall we know how it is a 4.5.2. Okay, so stability computation for 1 meter run of the wall. Okay, we need to calculate the stability computation for 1 meter run. Okay, now the first thing is that what is the distance of point of application of resultant from the A. Like in this diagram. Okay, in this diagram you can see, okay, in this diagram, sorry, where it is, in this diagram we need to calculate the distance of point of application of resultants from end A. Like from how much the resultant is acting at the point up to from A point, we need to calculate first. That means we need to calculate the distance. What is the exact maximum load is acting on the point, we need to calculate. We need to calculate the application of the resultant from this starting A point. Okay, so or end A point we can call it as. So for that there is a I just write second step, or I can write the stage over here, which is the second step for the stability calculation. It is like the Z value. We need to calculate Z distance, which is nothing but the 324, like this much distance. Okay, and 204 distance, like, okay, 327 from end A, like here this okay, here you get the all value after some time. Just I need to first check I need to prepare some stability calculation first, sorry for this. Okay, so first of all what we are going to do, we are going to calculate like how that Z value our final output is Z. Okay, we have to calculate that. So first of all you need to calculate the stability calculation for 1 meter run of the wall. Stability calculations for 1 meter length of wall. Okay, so how we will get it? So for that we need to just take the loads, we required loads. Okay, we need the magnitude of load. Okay, which is always in kilonewton. Then we need a distance from A, okay, which is nothing but in meter. Okay, then moment we required, which is kilonewton into meter. Okay, so maximum of magnitude of load, distance from A, and moment. Okay, now so first what is the load we have, like W1. Okay, W1, like here for steam is a W1. Okay, for a base is for a slab is W2, and here is what W3 for embankment. You need to watch my first video for that. Okay, so how we'll get the W1, like okay, now I just wanted to just repeat this diagram so you can simply understand the value first. Okay, wait a minute. Okay, so now we are going to calculate W1 first. So it is what our W1, right? So how the value is 0.2, like 200 meter, multiply by the height is total height, this much is height 4.75, multiply by the density 25. Okay, so for that W1 we will get, so it will be like 2.5, okay, 0.2 multiply by 4.75 multiply by 25. Okay, so we get the W1. So for W1 that the magnitude is what, 23.80. Okay, and the distance from A, like we need to calculate distance from that. That means this is a 1.55 distance. Okay, what we get the exact distance is like this, up to this is 1.65 distance from this one. Okay, so it is what, 1.65 distance. 1.65 distance we have, and the moment what we are getting, the moment, like whatever the moment we are getting right now, it is like the 39.27. Okay, so force into perpendicular distance. Okay, so magnitude multiplied by perpendicular distance, you get the moment. Okay, now second we are going to calculate the W2, but in W1 there is also one value, like we are not forget this value also, we need to calculate this value also. Okay, so it will be like W1 also having some another formula, that means a different value also, which is 0.5 multiplied by 0.25 multiplied by 4.75 multiplied by 25. Okay, so from that we get the 14.84, 1.83 is the distance from the top. Okay, and distance from A, and 27.15, like this I am talking about this much value. Okay, that is value, that this much value. Okay, that the remaining value over here. First we calculate to this one, then we are calculating this one value. Okay, now we are going to calculate the value for W2, and then we go for the W3. Okay, so for value of the W2 calculation is like W2 we are going to calculate. So here is what the total distance is, what 3 meter, 0.45 is the height, and 25 is the unit weight. Okay, so it is like 3 multiplied by 0.45 multiplied by 25 is the unit weight. So we will get it as 33.75. Okay, and the distance is what 1.50, you know properly, like up to this one is a 1.5, I take 1.5. Okay, so the moment what we get, it is 50.62. Similarly with the M3 W3. Okay, how will we get it? Like the 1.5, like this is 1.55. okay, the 4.75 is a height, and 18 because it is a embankment is unit weight is what 18 we are taking. So it is like 1.55 multiplied by 4.75 multiplied by 18. So we will get 132.51, and the distance is what 0.78. Now you take what is the distance are exactly, you are taking the difference. So what W3 is taking half right now here. Okay, so it is 0.70. When you multiply it, we get 103.35 moment. Okay, now we need to determine what is the moment due to the earth pressure. Okay, so what is the moment due to earth pressure, we also calculate. Okay, moment due to earth pressure, we need to calculate. So moment due to earth pressure is what, Cp multiplied by Wh cube by 6. Okay, so Cp is what we know 1/3 value, multiplied by W is what value 18, into height is 4.75 cube by 6. Okay, so the value is for moment due to earth pressure is, we also get it. Okay, so this is what after that, like don't worry about this. Okay, so what exactly this value will be right over here, 107, because this is a moment, 107.06. Now at the end of this all calculation, what we get the summation of the total load magnitude, which is nothing but 204.90, and the moment what we get is 327.45. okay, these two value we are getting right now. Now after that, when what I told you, like here what I told you, like the Z distance we need to calculate. Okay, which is nothing but the distance of application of distance of point of application. This is nothing but called as the distance of point of application. Okay, of resultant. From end A, मतलब यहाँ से, from here. Okay, so how it is like, it is like 327, that means the moment upon the load. Okay, so 327, okay, 327.45 upon the 204.90. okay, so we will get is a Z equals to 1.6. so this is what the resultant of the point of this, it is a distance of point of application of the resultant at the distance of 1.6 meter we get right now. Okay, so now we need to determine the eccentricity also. Okay, so what is the eccentricity we need to calculate? It is like the Z distance we have minus B by 2. Okay, Z minus B by 2. So it is like Z is what 1.6 minus what is B is like 3. What B is like this much distance divided by 2. So this is what eccentricity we will get. It is like the 0.1 meter. Okay, so so your eccentricity is always less than b by 5, b by 6. It is what a check. Okay, so remember your eccentricity is how much, 0.1, and b by 6 is getting 3 by 6, that means 0.5. So your check is okay. Okay, we can further proceed for a calculation. So now after this calculation, okay, when we complete this calculation, now we need to deal with the maximum and minimum pressure at base as computed. Okay, so what is the maximum pressure as getting as at the base? We need to calculate it first. So we are getting the maximum and minimum pressure. Maximum pressure at base. Okay, base. So okay, which is nothing but given by P max equals to 204.90 by 3 multiply by 1 plus 6 multiply by 0.1 divided by 3. Okay, so which is nothing but we get P max, okay, equals to 82.00 kilonewton per meter square, and P minimum equals to plus change by minus, so we will get 55 kilonewton per meter square. Okay, now after that in this diagram we need to draw these values. Okay, like the maximum minimum pressure. So here it is what we call the maximum pressure intensity, pressure at bed, the 55 kilonewton per meter square. Okay, sorry, per meter square over here, and sorry, meter square, and here it is what we get 82 kilonewton per meter square. Okay, so that is what exactly the thing I'm talking about. Okay, now after that we need to go for the design of the hill slab. Now in design of hill slab, all these things are required, because without this thing we cannot further proceed for our design of hill slab calculation. Okay, so now we are going to design our next step, like E step, which is nothing but design of hill slab. Okay, okay, so how we can do this problem? So just start from here. Okay, so what is the moment computation already we did in this table. Okay, you can see in this table what are the moment we get over here, 103, like 20490. Okay, all this moment we need to these are the required for our this next step, design for the hill slab. So here first we need to go for moment calculation first. Okay, and after that we will further proceed. Like we know up to the W3 calculation, like it is 132.50, we know the distance. Okay, now we go for the what is the self weight of the hill slab. Now here we are going to deal with only design of hill slab. So first we are going to moment calculate, moment computation. Okay, so in moment computation we are going to deal with only hill slab. So you take only the load of the what, hill slab only. Okay, so here are the what loads. Okay, then what here the magnitude of load. Okay, then we have distance from A, and we have moment. That means we need moment. Sorry, my English is not good. Okay, so now W3 is equals to, what is the W3? We already calculated, the value is 100 and sorry, we just write here 132.50. like we next in first table we calculate all the value 775, and this is what 102.68. Now we got for the self weight of the hill slab. What is the self weight of hill slab? okay, which is nothing but 1.55 is a length, okay, 0.45 is a height, okay, and 25 is what density. Simple. So it is 17.40 we get, okay, and the distance is same, 0.775, nothing is changed, and 13.51 is a moment multiplication, okay. Now when we get made the total of this, okay, that means what is the total, W3 plus 10, the load and the self weight, so we will get 116.19 kilonewton into meter, the total movement we get. Now we need to deduct the upward pressure, okay, so we need to deduct the upward pressure from that, that is of the pressure distribution diagram. If you know about, like, this is what the pressure distribution diagram for the hill slab, okay, we need to deduct the A, B, H and I, this much of the amount we need to deduct from that, okay. So no, I just it is a A, B, I, H, okay. So A, B, this is what J, actually we need to deduct J and H, this much amount we need to deduct from that, okay. So how it will be work? So it will be work in a such a manner that, like, the deduction, I just write over here, deduct the upward pressure, deduct pressure. I told you, like, which pressure we are going to deduct. We are going to deduct this much amount of pressure, okay. So it work like, the deduction is like 53.84, the distance what we already calculated, 53.84 multiplied by the 1.55, okay. So we will get the 83.45 at distance of 0.775. so we need to deduct it from, so we get it as a 64.67, okay. And after that, upward pressure at GHI, like, we first calculate, because this is a rectangular section, so we calculate it for first, then we calculate for GHI, for this section we for triangular we can calculate. So upward pressure for that also, okay, it is like upward pressure, okay, is like 0.5 height multiplied by 1.55 multiplied by 13.9, okay. So this much distance, okay, so this much distance is what the all 13.9, okay, and this total distance is what, that means this was distance is was 71.78, okay. And okay, so now you tell me, like, how you can get this all the value, buddy. It's very simple, like, this much distance, okay, it is what, 55, this is distance 82, so 82 minus 55 you get 13.9, okay. And if you minus this one, so you get 71.78, from 82 you minus this one, so you get 70, like, I just minus this distance, okay. So you get 71.78. it is very simple, don't worry about this, okay. So now after that, the upward pressure, like, this is 0.5, that means this much GHI, I am just dealing with this one, okay. Or I can write this name like ABJH first, ABJH, and this is what, HJG, okay. So now we will get the value is 10.77, okay. So here we it is at distance of 516, okay. So the distance, because it is at the inclined level, okay, so we get the value as 5.55 movement, 5.55. When we did the total deduction, like the total deduction, when we made total deduction when we made the total deduction, we will get the value as 70, as a that means this much, it is total day 40, this is the addition of this is what, 70.22, okay. So final is what, final is equals to this amount minus this, so we get that in 11619 minus 70.12, we get the 46, okay. So this is what the maximum working bending moment on hill slabs, okay. So we get maximum working moment hill slab, okay. So this is what, 46 kilonewton into meter we get, Okay, now after that we are going to do for the maximum design ultimate moment. Okay, now we need the maximum design ultimate moment for this. Okay, so now how we'll get the maximum design ultimate moments? Wait a minute. So now we need the maximum design ultimate moment. Ultimate moment, which is nothing but mu, okay, which is given by factor 1.5 multiplied with is 46. Okay, so you get the factor, okay, which is 69 kilonewton into meter. Okay, so it is like mu upon bd square. So we will get the, this is what, 69 into 10 raised to power 6 divided by what is b value is 10 raised to power 3 into 400 square. Okay, so like we will get the 0.43. this is the factor. Okay, now as per the table table 2 of SP, we need to refer the SP from table 2. Okay, so to read out, that means from this SP you need to refer this table number 2. So you table that is 16. Okay, 16. So reach out the percentage of the reinforcement. What is the percentage of reinforcement? PT. So you get the PT is equals to 0.121. Okay, percentage of steel you get. So from that we calculate the AST. Simple. Okay, what we called for the steam also. AST equals to PT BD upon 100. So you place the all the value. It is 0.121 10 raised to power 3 into 400. 10 raised to power 3 upon 5 into 100. So you get the value as 484 mm square. Okay, so hence I am going to provide, okay, hence I am going to provide the 12 mm diameter bars at 200 mm center to centers. Okay, so I am going to provide, okay, you can see, yes, you can go, I am going to provide 12 mm diameter of the bars at 200 mm center to centers. So we get AST equals to 565 mm square when you put the in this formula. AST equals to number multiplied by pi by 4 into diameter square. So when you 12 in this formula, okay, 200 mm 200 mm spacing, yes, distance, so you get value, or 12 into number of bar you place, you get the AST. Okay, now so distribution reinforcement we need to calculate. So distribution reinforcement I need, so it is like the 12% of 1000 multiplied by, okay, so 12% multiplied by 1000 multiplied by 450 width, so you get the value as 540 mm square. This is the distribution steel. Okay, now I am going to provide, with respect to distribution steel, I am going to provide the 12 mm, okay, 12 mm diameter of the bars, okay, at the rate of the 200 mm center to center. So when I get the AST as equals to, so with respect to this I am getting like required distribution steel is for 550, but according to this value my steel is coming 565 mm square from this formula. Okay, so now up to this I am complete with the design of the hill slab. For design of hill slab we are going to require the 565 mm square steel, okay, and we need distribution steel as a 540, which is we calculate as a 565. The total steel what we are required is 484, okay, like for a main steel. Okay, so I think guys you that means we are done with this all the data right now. So I hope that we will conclude today this we will continue this numerical in step number 3, like part number 3, which is all about the design of toe slab and check for safety against sliding. And in next part we will go for check for the shear key and the final output. Okay, so please visit my channel and subscribe my channel, like my video. visit my website, and thank you. Have a nice day. Bye bye.